I welcome you to this video. Today we will implement the arithmetic unit, which is this model here. The last time we implemented a control unit, and we see here we have some connections here from the control unit to the arithmetic unit, like the operation, the immediate value, or the enable. For what they are, I also explained in the last video, but again, for the repetition, we have here an operation so that we know what we want to do here. So maybe we want to add these two values here together or subtract them or do something else. Then we have here an immediate to add maybe something to a value which we get from the operand 1. Or we have the enable, and this enable is used to tell the arithmetic unit that we have a new instruction. And when we have a new instruction, we can update here the flags and store these flags, and then we store them until we get here the next enable, and then we can update here the flags. Then the result we give back to the register model, and here in the register model, when the enable result is set to 1 and the destination is set, the result will be saved here in the corresponding register. And here we also have some interfaces for the operand 1 and operand 2. So here we get these two operands, which we want to add or subtract or do something else. And also a clock and a reset we have. So let's start to implement this. And before I start, as always, I first make a short git commit. The last time we implemented cd. We implemented the control unit, so let's make git status. And we see here, we have here the control unit, and here also some other changes, but that's okay. So let's say git add -- all, git status, and now we should see everything is in the staging area. And then we can say, okay, git commit -m, and say here comment implemented control unit CPU control, and that's already it. And so now we can start open our project. We see here we have already our models, and we want to make here a new source, add or create design source. Yes, we want to create one, and we name it CPU arithmetic unit. Okay, then we want to have it in the MCU lib. That's okay, finish. And then as always, we can copy here the things from the ROM code, that we do not have to write everything new. So let's copy that and open the arithmetic logic unit, paste it in here, and now we can rename it CPU_Alu. Then we do here and here, and then we can actually start to implement our entity. We saw we have a clock, and we also have a reset, which is also an input of the type std logic. Then we have an alu in signal, which is of the type control unit to arithmetic logic unit. Then we have an alu output, which is an output of the type arithmetic logic unit to control unit. An operand 1, which is also an input of the type std logic vector, from data with -1 down to 0. And the same we have for the operand 2, which is also an input std logic vector, data with -1 down to 0. And we have a result. Here I forgot one bracket. Result which is an output of the type std logic vector, data with -1 down to 0. And that's already it with our entity, and here down to has to be written correctly. And here the last semicolon I do not need. Then we can create here different signals, one for the Alu operand 1, which is of the type std logic vector, data with -1 down to 0. And the same we have for the operand 2, and then also for the operation. And this is not data with, but here first Alu operand address with -1 down to 0. Then the same for the result. For the set immediate, from immediate operand word width -1 down to 0. And then the same for add immediate low and add immediate high. And add immediate high. Signal Alu enable is of the type std logic. Signal operand 1 most significant bit is also of the type std logic. This we need for the flags. The same for operand 2. Then a signal operation 2a for addition most significant bit of the type std logic. Then a signal for the most significant bit of the result. And a signal for the flags, the flag array. Then some constants for the sign extension is of the type std logic vector. Immediate operand word width -1 down to 0, and is everywhere 0. So others 0. And the same we do for 1. So we want to extend everywhere with 1. I can say that. Yeah, and then we can already begin with our default assignment. Alu out dot flag n is equal to flag n, and the same we could do for the auto flags. Here I forgot everywhere the a, set overflow, and also the carry, and the Alu operand 1. And here I wanted to write operand. So let's change this. Is equal to operand 1. And the same for the second operand. Operand 2. And the Alu operation is equal to Alu in dot operation, and the set immediate is equal to Alu in that immediate. The result is equal to alu result. This delete. Then the add immediate high is equal to alu in dot immediate and sign extension 0, add immediate low is equal to extension 1 and alu in dot immediate when signed alu in dot immediate is smaller than 0, else extension 0 and alu in dot immediate and alu enable is equal to alu in dot enable operand 1 underscore most significant bit is equal to alu operand 1 data with -1. The same for operand 2. And then also for the result most significant bit is equal to alu result data with -1. Yeah, now we can actually start to calculate our result, and for that we do not need a sequential process but a combinatorial one. So we can say the following: with to integer unsigned alu operation, select alu result std logic vector unsigned alu operand 1 plus unsigned alu operand 2 when 0, and when 1 we want to do the subtraction, so minus here. Then we could say others zero bracket when others, and here we do not need brackets, but only that. And yeah, then we can add more instructions like or, XOR, and so on. Alu operand 1 and alu operand 2 when 2 and alu operand 1 or alu operand 2 when 3 and alu operand 1 XOR alu operand 2 when 4 alu operand 1, data width -2 down to 0 and 0 when 5, and Alu operand 1, data width -1 and -1, and Alu operand 1, data width -1 down to 1 when 6, so that were the shift commands. Then Alu operand 1, then 7, and std logic vector Alu underscore operand 1 plus unsigned at immediate low when 12. And here I also have to write an unsigned. Then here I can close the brackets. Then the same thing for immediate high. Then Alu operation 1, data width -1 down to immediate operation word width and set immediate when 13, set immediate and Alu operation 1, immediate operation word width -1 down to 0 when 15, and yeah, the others we can let how it is. So that are actually the calculations or Alu can do at the moment. And now we can also do the flag settings. And here we said we want a sequential process. So let's say process flag if rising edge clock, and here we first ask what the reset state is. If reset is equal to 1, then all flags are 0. So we say all the flags are 0. And then if rising edge clock, then if Alu enable is equal to 1, then could I actually end if flag n is the most significant bit of the result, and flag set is equal to 0. And let's make that a little bit nicer. So then if to integer unsigned Alu result is equal to 0, then and if flag set is equal to 1, So then this value here is overwritten because we are here in a process. Case T Alu instruction value to integer unsigned Alu operation is end case when others we can say null, when add immediate low or add immediate high, then flag C is operation 1 most significant bit and operation 2a underscore most significant bit. And operation 2a most significant bit you have to define. So let's do that before this process with the Alu instructions. Value to integer unsigned Alu underscore operation is select operation to a most significant bit is equal to Alu operation data with -1 when add immediate low data with -1 when add immediate low and add immediate high data with -1 when others. Here Alu operation 2, and here we need to set commas. And then this one is set, or operation 1 most significant bit and not result most significant bit, or operation 2a most significant bit and not result most significant bit. And the flag for the overflow is equal to the following: not operation 1 most significant bit and not operation 2 most significant bit and result most significant bit, or operation 1 most significant bit and operation 2a most significant bit and not result most significant bit. When subtract, then and here we forgot this. Copy this here, operation 2, operation 1, or and not, or result and not operation 1 most significant bit, or operation 2 most significant bit, and result most significant bit. And here operation 1 most significant bit, and not operation 2 most significant bit, and not result most significant bit, or not operation 1 most significant bit, and operation 2 most significant bit, and not result most significant bit. Oh no, the not we do not need. And that's already it. So we implemented here also our LU. And I hope this will work. I also write here no test bench, because also here the effort would be too large. We will test in the end the whole thing. So now we only have to implement the bus and the register model in the next video. Yeah, and that was it. I hope you learned something. I mean, what I made here. That's quite complicated. That is the flag setting. I mean, you can study it yourself when happens a carry and overflow. Yeah, you can study this by yourself, but I will not exactly go through here. And this was it from this video, and I hope I see you in the next one.